similar results. So what happened here was that the critic was, so instead of the human we have a critic, but in this work the critic was fairly simplistic. So it wasn't really looking at the image directly, it was just looking at some statistical features of the image. So the artist would generate the image, and then we would use libraries from OpenCV to extract out some properties of that image. You know, the entropy of the pixel intensities, or the size of the second largest blob, or these sort of things. You extract out about 15 or 20 standard statistical features, and then you feed it into a genetic program or a small little two-layer neural network. And the images that resulted from this, they have a certain naive charm about them, but they're a bit hokey looking, and we think the reason is because the critic was too simple to really make a good determination. Okay, so the story then moves on to GANs. Now I'm not going to say too much about it because Sage is going to go into much more detail, but the idea with these generative adversarial networks is instead of calling them artist and critic, they call it generator and discriminator. And the discriminator is one of these convolutional neural networks that's been used in recent years for image classification. So the discriminator takes in an image and comes out with a number, in this case, just a single number, and it tries to, if you just go back to this, so the critic is trained to try to assign a number close to 0 when it's fed with a real image, and a number close to 1 when it's fed with a synthetic image, or the other way around, to discriminate between the two. And in the case of GANs, the generator is also a neural network. So it's kind of like the reverse, the order of the discriminator. It starts with these latent variables that are chosen from a Gaussian distribution, goes through some fully connected layers, some deconvolution layers, and produces the image. I haven't shown the discriminator, but the discriminator will be the mirror image of this. The image is fed into the discriminator, and you actually do the backpropagation from the discriminator back into the generator. And this is the equation that is, the discriminator is trying to maximize this, and the generator is trying to minimize it. So this is this term here is the term on the left is the expected value for the real images of the log of the output of the discriminator, and the term on the right is the expected value for the generated images. So you can see this is trying to get the discriminator to maximize one of those and minimize the other. The generator doesn't have any effect on the first term, but tries to generate images which to which the discriminator will assign a high value. Now these are some, these are very old, this is from a couple of years ago, but this is some of the images that can be generated by GANs of bedrooms, and you can see these are all synthetic images, and you see they're quite realistic. And one of the reasons that GANs work well, I guess this really goes to the nub of the matter, is that famously neural network image discriminators can be fooled. You can take an image and it'll classify it as one thing with high confidence, and then you add some noise, you add something to that image that the human doesn't even notice, but the network suddenly thinks that it's in a different category. So the reason that the GANs solve this problem can be thought of again as back to this like leopard and gazelle. That basically, let's say there is a weakness in the discriminator, that it can be fooled into thinking that it's a different category, then what will happen is the generator will adapt to try to exploit that weakness, but then the discriminator will react in response to try to correct that weakness. So it's kind of a self-correcting mechanism. Okay, so now I wanted to move on to this evolutionary arc project. Now what we did with this is that it's kind of a hybrid between the artist-critic coevolution and the GAN. So what we do is we replace the critic with a convolutional neural network. So we have a convolutional network that's trying to discriminate between the real images and the synthetic ones, but our generator is not a neural network, it's actually a genetic program, and it works in the same way as Carl Sims's system as a function. So each of these images, you specify an x and y value, so the x values range from -1 to 1, and the y values range from -1 to 1, and you feed in a particular x and y value, and it comes back with 3 values which specify the red, green, and blue intensity at that point, if it's a color image, or just one value if it's a black and white image. Now, the details of the genetic program, again, aren't particularly important. It's just, it's basically just a program that's written in a special kind of language that's specifically designed for evolution. And this language, this agent has a memory and registers and a stack. And so there are commands for input and output. There are commands to manipulate the stack, mathematical functions, registers and memory functions, and branching instructions. So you kind of put all this together and you get a program that computes some function. And we also use this thing called hierarchical evolution, where we just, instead of having a large population, we have a small population of competing agents, but we have a bigger kind of genetic pool of agents that are recently deceased, that are still available for breeding. So some people have suggested we call this necrophilic evolutionary computation, but that's a bit morbid, I guess. But the main thing is that the fitness function is a bit expensive here because it involves feeding the image to this convolutional network. So it's important to try to keep the population fairly small but still preserve diversity. Okay, we've applied this framework previously to control tasks and classification and string processing and other tasks, but here we're looking at image generation. Now for the critic, we tried a couple of different kinds of critics, which were simplified versions of traditional image classification networks. So one of them is a simplified version of the Linnet 5 model, the other one is a simplified version of the 4 convolutional network. So this second model is a bit slower, but is perhaps more accurate. Okay, so the way this works is that the system basically sits and generates images one after another. So it generates maybe one image every 5 minutes or something, and so it in the very first round, the critic is you just start with a blank image to get you started. So the first critic is just trying to distinguish between a blank image and the reference images, and then an artist is evolved to try to the first critic becomes the fitness function for the next artist. So the artist tries to generate an image which the critic will classify as a real image within some tolerance. And when it reaches that tolerance, or when a certain number of generations are exceeded, you stop that evolution and produce that image, and then the next critic is trained at all. Each critic is trained on all previous images. So what typically happens is, the first few images are very simple. They're just sort of solid colors, and then you get into things that look a bit like flags or stripes or circles, and you just get this gradual kind of increase in complexity as the system progresses. Now, one of the benefits of doing this thing as a function is that you can upscale the images. So the critic is maybe built to only accept a 28 by 28 image. So the thing on the left is what the critic actually sees. But when we find an image that we like, we can re-render it at a higher resolution if we find it more appealing. Okay, so let me just show you some of the images we generated. So the first experiment we did was the real images were handwritten digits, and we found that sometimes, after a while, it did sometimes produce things that looked like digits. They preferred certain digits like 0 and 8 over others, and it's sort of in the early stages, it produced quite regular looking shapes, and then I think the critic kind of detected the regularity and realized that these things were too regular, so then the artist had to sort of make them a bit more twisted in order to fool that critic. And then you also get some images like this which don't look like any particular digit, but just sort of look like a sort of few different digits. But the other interesting thing is sometimes it produced things that didn't look like a digit at all, but may have a certain kind of artistic merit to them. So, particularly like this one that looks like a digit that fell in the water and got wet. Now, so we started out with the digits. Now, our second set of experiments, we moved on to this CIFAR 10 data set, which is a database of low resolution objects in 10 different categories. And here's some of the images that emerge. And one of the interesting things here is like, often they don't, sometimes they look like everyday objects like a wine glass or a spoon. Sometimes they look like these sort of freakish fantasy landscapes. Sometimes they look a bit like Art Deco designs. But it's sort of this work in a way, so in other words, you start with an image, you train it against images of a dog or a truck, but you might actually get something that looks like a Christmas ornament or something. But there's something interesting going on here. I mean, I think this is related in a way to this idea of Russell Standish and Ken Stanley of novelty search or like evolution without an objective function. So here we do have an objective function determined by the reference images, but in a way the details of the reference images might not be quite the important thing. Maybe it's more important the fact that each critic is trained to reject all previous images drives the system somehow towards greater complexity. And if you allow sort of subroutines and longer programs, you get slightly more involved images. Now, all these images were trained on all 10 categories. If you narrow down the scope of the images, you get slightly different results. So these images were evolved just trained against only the images in the ship category. So we do tend, that gives you a better chance of getting things that look a little bit like a ship or a nautical object. And more recently, we've been doing some other experiments. So these images are evolved against, images of the Eiffel Tower. And this kind of looks a bit like Andy Warhol's pop art. But you see the variety here of different colors and textures, and sometimes in this case the tower is actually missing, but it's created everything else okay. We've got a bit of a Chinese pagoda in the corner. This image in the middle, it's actually tried to recreate the texture of the tower using fractal geometry, and I think one of these even has a bit of punctillation going on. Now sometimes we get a bit more abstract results. So these images, these are evolved against images of another famous world landmark. Does anyone want to guess what that is? The Golden Gate Bridge. You knew it was the Golden Gate Bridge. I mean, again, we're getting into a weird area here. I mean, none of these really look like the Golden Gate Bridge, but they do somehow maybe recreate some aspect of it. Yeah. This one's a bit closer to home, maybe.
Opera House?
It's in the Opera House. Yeah, so again, this one's sort of more simplistic in a way, but you see how it tries to recreate the reflection on the water and the pattern in the clouds. And finally, this one's evolved against a single image of a famous painting. Does anyone want to guess? I told you it was famous. So again, I mean, it depends on your own personal taste. I personally find this quite interesting. I mean, you can't, there's no face here, but somehow this does suggest to us a woman looking sideways. I don't know. It's a bit like Cubism or Picasso, and actually, sort of what the system's actually being given something at much lower resolution. This is what the system actually was trained of. Okay, so just a couple of more remarks to wind up. So, sorry, I should have said this is joint work with a couple of my students, Jacob Sodal and in particular. Now, so in my group, Alex Long is here, and we had another undergraduate, Xuan Tong, who's been looking into this area. So we found a paper from last year in which, so some of you are probably familiar with this deep Q learning for Atari games, but we found this paper in which it was proposed to actually use imitation learning for this kind of task. So what happens here is that a human plays the game and you collect the information about all the states and what the human did, and then the agent then is presented with the same states and chooses actions, and a critic, the discriminator, has to try to guess whether that action was done by the human or the agent. So the equation here is actually almost identical to the one for GANs. There's a bit of an extra term here to increase the entropy.